Hello, everyone, and welcome back, or welcome to, depending on if you've been with us or not, to EE World's Engineering Training Days. Really happy that you're here to join us for our next training day on Don't Let Moisture Win, Venting Approaches to Improve Reliability in Electronics. And that is sponsored by GORE. You'll hear from our presenters in just a bit, but you have to stick with me right now, okay? So there's some tools available for you. There's resources that can be downloaded in the resource widget. There's at least a few white papers. There's also links to the previous webinar that GORE and EE World did together, as well as the one that's coming up on December 4th, but we can talk more about that later. Just know that there's resources for you. And you can submit a question in the Ask Question widget. If you're watching this on demand, you can still ask your question. So go ahead, post your questions, and then when we get to the end of the presentation, we will start asking them. Also, you can expand the slides with the icon in the top right-hand corner if you want the bigger picture. Now, should you have any issues during the webinar, just refresh your browser. That solves almost all of them. Try closing out the other apps and browsers. They can be bandwidth hogs. There's a help in the top menu for troubleshooting steps, but that Ask Question widget that I mentioned, you can always put something in there and our esteemed webinar producer will help answer those questions. So I'd like to now just introduce our speakers from GORE and Associates, starting with Michael Schindler. Michael is the Electronics Applications Engineer with GORE. He earned a master's degree in chemical engineering from TU Munich in 2015. During his studies, he gained valuable experience in the automotive industry, including his master's thesis at BMW. He acquired extensive expertise in plastics and polymer testing while working as a specialist at an independent laboratory and later as a laboratory engineer at W.L. Gore and Associates. At Gore, he contributed to the automotive and packaging venting division, focusing on advanced testing methodologies. In 2023, Michael transitioned to the Gore Electronics business as an applications engineer, leveraging his scientific and engineering expertise to support customers and deliver solutions. And we have Alec Kritau. Alec is the electronics applications engineer, also with Gore and Associates. And with nearly a decade of experience in quality assurance and engineering, Alec is a dedicated professional committed to innovation and problem solving in the automotive and electronics industries. As an application engineer at W.L. Gore and Associates, Alec drives growth in the electronics market, discovering new and upgraded applications for unique materials to enhance everyday life. So we've got two experts here. Make sure you take advantage of your opportunity to ask them questions. And we are going to start with Alec, I believe. So Alec, it's all you.
Thank you, Amy. Hi, Alec Critter here talking. Today, we'll be sharing more about venting approaches to improve reliability in electronics with a special focus on moisture and moisture management. I will be presenting with Michael here. Just wanted to share a little bit more about GORE. You may have heard of the popular Gore-Tex brand, a waterproof and breathable fabric used in outdoor sporting applications. It may be familiar in your life. So with that, I'd like to start. I want to set the stage. Today, our world is connected through electronic systems. We rely on electronics every day for everything from convenience, but also for our safety and security, including cameras, sensors, meters, lighting, and Wi-Fi devices. And every year, this equipment gets smaller, more powerful, and is expected to operate 24 hours a day for 7 days a week for years. It's crucial that our systems remain operational and protected from the elements throughout their lifetime. Failure is simply not an option. So I'd like to recap from our previous webinar. If you did not get a chance to watch it, I invite you to watch the recording. In summary, we have a microporous membrane at the heart of all of our vents. This membrane enables pressure equalization, which is needed due to constant temperature changes from working electronic components, but also due to environmental changes. At the same time, this membrane blocks contaminants and keeps the interior of the enclosure clean and dry, as you can see in the depiction on this slide. At the end of that first module, we showed this slide stating that a vent can also be used for moisture management. So in this webinar, we'd like to dive deeper into that topic uh, in showing how a membrane vent can help to mitigate common moisture-related failures in the field. We need to manage this moisture. So I'd like to kick off with a poll question. If anyone has had to consider condensation management in the design of your enclosure, give you about 20 seconds to respond. Okay, we have a few responses, so the results. It's like a very popular topic. Condensation management is important. And if it is not something you've considered, well, I'd like to share more about why it would be important to consider condensation management when designing your electronic enclosure. So, I'd like to touch on a few of the consequences where moisture ingress can become a problem with improper design and or improper venting. The condensation can prevent the device from functioning properly overall, whether it's a camera lens or a photocell sensor as shown in the left-hand photo. That internal moisture could lead to corrosion, total device failure as shown in the middle. But also, the aesthetic of a device could be degraded due to moisture ingress, such as in these connectors. All of these could harm your brand recognition, and we, of course, would like to avoid that. So, of course, there are many options to deal with moisture ingress. Most of them have pros and cons. We believe that a vent is the best way to manage all of them, and this is why. A desiccant, well, it does a great job at removing the moisture, but only for a short period of time. It needs to be changed out, or it can complicate moisture management even more when it is fully loaded without proper maintenance intervals. A heat source could be used, and that does prevent condensation, but it doesn't tackle the root cause of moisture entering the enclosure. It also needs an energy source to run. If it is primarily just for managing moisture, it might not be the most efficient uh, solution. A fan and a filter could drive out moisture effectively, but the filter will block the moisture movement over time, and the fan also needs energy to run. And filters typically have bad ingress protection against liquids, I would add. Fully sealed enclosures, well, moisture can get in through sorption, but there's no way out. It would be trapped inside that enclosure. And of course, as we touched on in the first webinar, seals can break and lead to additional moisture ingress over fatigue and stresses of the environment over time, which is why we propose and insist that venting is the best solution for managing condensation. And I'd like to add that condensation is a natural phenomenon. It cannot be prevented all the time. The key is to manage condensation as much as possible. So, in order to manage it, you need to consider multiple factors, including proper venting. So, in the next 15 to 20 minutes, Michael will introduce these factors, show you why they are important, and how you can use them to your advantage. Michael, I pass it off to you.
Thank you, Alec. Yeah, so now I want to introduce you to the physics of moisture transport and the theory behind moisture management. So I want to kick this off and explain some basic terms with this example. So here you can see some graphics, and on the left-hand side, the first graphic would be an enclosure with a defined amount of absolute moisture indicated by the water column. So the amount of air that the amount of moisture that air can take is dependent on the temperature. So at 22 degrees C, the amount of moisture that you see corresponds to 50% relative humidity. If you would cool down the system with the same amount of moisture, you would end up at 77% relative humidity. And if you cool it down even further to 11 degrees C, then you would reach 100% relative humidity. And this is actually the definition of the dew point. The dew point is the temperature at which a system has a relative humidity of 100%. If you cool down a system below its dew point, the relative humidity will still stay at 100%, but the glass in this example will spill, and the spillage will be condensate. So this is theory, but in reality, there are different factors that can influence condensation formation. There are some factors that you can influence quite to influence, as you might see. Our perspective, the easiest way to influence would be adding a venting system. So there are different characteristics of a venting system. There are different types of venting systems. For example, there can be just a weldable disc, a disc with a membrane ring to glue and to stick the membrane to a housing, or there are molded versions where you can screw or snap in the membrane to your housing. And all these versions come with different materials. There can be pure membranes, or there can be laminates, so different materials for the venting system. All these materials and types, of course, have different performance characteristics. And another very important topic is the positioning, but I will cover this later. The second important topic that is hopefully also slightly influenceable is the material selection and the thickness of the material. So this can be the housing material, but also materials from components inside the housing, like cables, a PCB, or other functional components. These components lead to the design and the geometry that the device has. So typically it's not just an empty square box. There are different cavities where the components are inside. There are gap sizes between these components. And as some of the components typically generate heat, there are hot spots and there are cold spots inside the design, which leads me to the amount of interior heat gain. So typically modern electronic devices, they are stuffed with temperature emitting or energy emitting components. And of course, as engineers, we want to optimize our systems. The components get smaller and smaller, and we pack more and more of them in the same space, leading to more and more interior gain inside the enclosure. And of course, as you want to have this optimized system, you probably are not willing to influence this and say, nah, I'm go with a lower heat device because it's better for moisture management. No, you want the best performance of your device. Therefore, you probably cannot really influence the amount of interior heat gain. And last but not least, oftentimes these components are used in very harsh external environments with changing temperatures, fast temperature drops caused by wind or rain, something like this. And if you ever find a way to influence this, so please call me, I would be very interested. So with this being said, I would pick up the next poll. So what do you think is the biggest contributing mechanism to condensation formation in an electronics enclosure? Is it sorption, permeation, diffusion, or sublimation? Again, I give you around 20 seconds to dig up the knowledge that you might have learned in university. At least I remember some courses where I was tortured with some of these terms. And then if you have clicked, I look for the answer, and we have quite a mix of sorption and diffusion. Nobody decided on permeation, and everybody probably remembered that sublimation means that a solid goes to the gas phase without hitting liquid state. So of course sublimation is not correct. Yeah, these are both very important factors, and in the next slides I will give you the answer. So what are the primary sources of moisture and the factors? So at first there is of course the sorption. What is absorption? Sorption means that moisture, water molecules are bound to the surface of the material. So typically for plastics material, this is a heavy influencing factor. So the amount of moisture that can be bound to a plastic surface is dependent on its temperature. At lower temperatures, more moisture can be adsorbed to the surface, and at higher temperatures, less moisture can be adsorbed to the temperature to the surface. What means if you increase the temperature of a system, the surface can hold less moisture and will release the moisture it cannot hold anymore, and therefore increase the internal amount of moisture. The next factor will be permeation. Permeation means that moisture will diffuse or permeate through the enclosure material to the inside of the enclosure. This means it's not just the moisture that is already inside, like for the sorption, but additional moisture will enter the enclosure through the housing. And last but not least, there is the diffusion. For venting with membranes, the diffusion typically happens through the vent. So this is based on a concentration gradient. If there is more moisture inside, the moisture will diffuse out of the enclosure. And if there is a higher moisture content outside, it can also diffuse inside. But I will explain this in greater detail on a later slide. Next, I want to show you an example for sorption and permeation. So on the right-hand side, you can see a graphic from a test that we performed in our lab. We dried out 3 different headlamps at a very high temperature for 6 days. And after that, we took regular weight measurements. We just let it sit in the lab and measure the weight difference of the headlamp without any additional moisture source, just lab conditions. So you can see within a very short period of time, all 3 headlamps picked up about 2 grams of moisture. So this is the sorption of the plastic materials. You cool, or the material gets cooled down so they can pick up more moisture, and therefore the headlamp will gain some mass. And you can see with the days, it's not stopping. The moisture will be picked up more and more. So this is then the permeation. Over time, the plastic material will pick up more and more moisture. And you can see for headlamp 1 with the yellow curve, even after 4 months, it is not nearly saturated. The curve is still rising and the mass is still getting higher. So what does this mean? This really shows that the plastic materials, and in this case, the headlamps were weighing around 5 kilograms, and 5 kilograms of plastic can hold more than 5 grams of water. And now if you compare this to the air inside of this headlamp, this is only 0.1 gram of water. So here you can see that the most amount of moisture, the main moisture source, really comes from the plastic materials. And if you desorb or if you heat them up, this moisture, the moisture will desorb again, and you will quickly release 2 grams of moisture in this case. There are differences between the different kind of plastics. So here on the left-hand side, you can see the water absorption for different kinds of plastics. On the right-hand side of the graph, there is nylon or polyamide. So you can see this is really the plastic material that you want to avoid when you deal with moisture, because this can hold a lot of moisture, and if you heat it up, it can also release a lot of moisture that will end up inside your enclosure. On the left-hand side, there are, for example, polypropylene or polyethylene, which are much more favorable when you think about moisture management. On the right-hand side, you can see some permeation statistics. So PMMA and polycarbonate are, for example, not very good when it comes to permeation. And this is particularly interesting if you think about when will you see condensation from the outside if there's a clear plastic type. And now polycarbonate and PMMA are the 2 clear plastic types. So here becomes obvious that permeation can be also a challenging factor when you're designing with clear plastics where you can really see the condensation from the outside. So choosing the right plastic material with a low sorption coefficient and a low water vapor permeability reduces moisture in the enclosure. And next, I want to cover the third mechanism with diffusion. Diffusion is typically based on Fick's law of diffusion. So the diffusion rate, the amount of moisture that is diffusing, can be described by a diffusion constant, the surface exchange area, and the concentration gradient, which is the concentration difference. And the difference here is really the absolute moisture, so the absolute humidity. And this is by the distance between the 2 concentrations. So there are 2 things in this that you can influence. The diffusion constant cannot be influenced. The concentration gradient typically also cannot influence because it's just the nature and the environment you're in. But you can, with a vent, increase the surface exchange area, and by proper placing of the vent, you can influence the distance between the concentrations. So these are really 2 factors that you can consider, and how vents can help you with this. This is something I want to show you on the next slide. So here you can see 3 different vents: a molded vent, an adhesive vent, which has slightly a larger area than the molded vent, but overall it's very similar to the molded vent, and a larger adhesive vent. So if you look at the diffusion value for these 3 vents, the molded vent and the small adhesive vents with the same size have similar or almost the same diffusion rate. But if you increase the area, in this case, the area is increased by 5, the diffusion rate significantly increases, and you can transport more moisture out of your enclosure by increasing the vent size. And oftentimes, people look at data sheets for vents and they see an airflow value on the data sheet. So they think that if there's a high airflow value on the data sheet, then the diffusion has to be high, isn't it? But if you look at these airflow values and you look at the molded vent, which can have an airflow of up to 7,600 milliliter per minute, this is very high airflow vent. And then if you look at the airflow value for the large adhesive vent, it is only 356. So this shows that the airflow value is not relevant for moisture management, because the airflow value is based on a pressure differential, but for typical moisture management use case, you don't have a differential pressure. You just diffuse without a differential pressure. So here the size really has an effect, like Fick's law proposed. With the larger area, you will get the higher diffusion rate. And we performed an experiment to really show this. So we did an experiment in our lab where we took 4 glasses of water and we just dyed the water into blue for better visibility. And you can see on the left-hand side, there is a sealed glass. Then we have the molded glass with the super high airflow, the smaller adhesive vent, and the larger adhesive vent. And take a note that all glasses are filled up evenly, and we'll just let these glasses sit in the lab for 21 days. And with the upcoming video, you will see what happened. So this is a time lapse of the experiment, and you can see on the right hand side with the large adhesive vent the amount of moisture or the amount of water in the glass is rapidly decreasing as the moisture is being removed from the glass by diffusion. There is only very little water removed from the middle 2 glasses, and I can hit this again for you. I hope it works. Yes, it does. And as you can see, for the sealed glass, the only thing that changes, there is condensation. And I hope this is a really nice way to visualize how vents can lead to different amount of moisture diffusion out of an enclosure. I also mentioned positioning. So we have some general positioning recommendations for vents. So typically we would mainly recommend having it on a side wall or on the bottom, so there is no pooling of water on the membrane, and we don't recommend a top mount, really for the purpose that there is no water pooling on top of the vent. But if we're talking about moisture management and condensation, there are some more specific placement recommendations. So again, we did a little test on the right-hand side, and you can see without a vent, we will have nice condensation creation. And on the middle picture on the left-hand side, we added a vent only on the left, and as proposed by Fick's law, close to the vent, there is no moisture, no condensation left. And at the bottom picture with 2 vents, one on each side, we will minimize the diffusion path, and there is no more condensation. So this clearly shows, at least from my perspective, that condensation, which is a physical and natural phenomenon that cannot be prevented, it must be managed. And I hope I could show you that by minimizing sorption permeation through the plastic and the proper selection, you can achieve this. And by optimizing the diffusion through proper venting, you can optimize your system for condensation. And up next, I want to go to testing, but at first it's again polling time. So my question is, do you have a way to create condensation for testing in your lab? yes, we use a protocol to test for condensation, perfect. Or B, no, I can only create condensation when I take a hot shower. So again, 20 seconds for you to vote for having a shower or create condensation in the lab. And I go to the solution, and it seems like a lot of you people want to take a shower. And luckily, even 70.6% have the opportunity or they use a test protocol to test for condensation, which is really great. So I want to show you how we do it at GORE and why we do it as we do it. So here you can see our test protocol for what we call our GORE 70C test. It consists of 4 different steps to ensure a reliable and consistent and repeatable test result. So at first, we want to open our enclosure, and then we will dry it at 80 degrees C for 1 day. So we dry it at first to get rid of the history of the test device. So just imagine one part is being shipped overseas, lots of moisture for a long time. So the moisture, the plastic material really picked up a lot of moisture. And the second test device would be sitting in the lab, only very little moisture, and you want to compare these 2 parts. So you need to dry them at first to get rid of this history. Then, in the next step, you want to bring in a repeatable, consistent amount of moisture. So we expose it to a environment of 23 degrees C, 70% relative humidity for 2 days. And the enclosure is still open, so the moisture can distribute evenly across the whole enclosure. And then after these 2 days, we will close them. And we will heat up the device to simulate heat, either by temperature changes and by the sun, or also by interior heat gain. So we just simulate 70 degrees C. And as you hopefully learned in the last minutes, what happens if you heat it up? Moisture will desorb from the plastic and will increase the dew point inside the enclosure. And now with this setting and the increased dew point inside the enclosure, we will spray it with a 10 degrees C water spray to create condensation. And this would be the outcome of this test. Again, we tested a headlamp because it has a neat, clean, visible surface that you can observe. And you can see after the spraying and wiping the headlamp, there is heavy condensation on the whole lens of the lamp. And we also brought some measurement probes alongside so we can really measure what happened here. So the red curve shows the surface temperature of the lamp. You can see it came in on the left-hand side with about 23 degrees C. Then we did heat it up to 70 degrees C. And then we cooled it down with the spray to 5 degrees C. And then it was just sitting in the lab again. The dark blue curve shows the internal dew point. Again, we come in with 23 degrees C, 70% relative humidity, which correlates to a dew point of about 80 degrees C. And as we start heating up the lamp, the plastic will release moisture and the dew point will increase. And then if you cool down the lamp, the surface temperature will drop below the internal dew point. And this is the clear sign that condensation will form. And this is what we see after all. And as we did the drying and the preconditioning step, the result is very repeatable. So this was a lab test. We also have a outdoor environmental real life test that we have on our roof for 8 years. So you can see we have different enclosures with different vents on our roof, and we also have an unvented reference enclosure. So we put temperature and pressure probes and humidity probes inside each of these boxes. So you can see different things from this. On the top graphics, you can see what a vent typically does. It reduces the internal pressure. So in the left graphic, you can see the graphic of the reference enclosure with a wide bandwidth of internal pressures from minus 130 millibar to plus 170 millibar, and a very narrow bandwidth of internal pressure for the vented enclosure. But you can also see on the bottom graph that on the blue curve, it shows the relative humidity of the unvented box and the relative humidity of the vented box in red. So the moisture from the vented box is driven out of the enclosure through the vent. Therefore, the relative humidity inside the vented enclosure is lower than the relative humidity in the unvented enclosure, showing the real life benefit of the vent when it comes to moisture management. And with that, I want to push it back to Alec.
Thank you, Michael. Thanks for such an in-depth discussion and sharing more on the mechanisms of moisture transport and ways to help mitigate it. I'd like to expand further into some field stories where GORE vents have helped customers mitigate moisture management, mitigate condensation, I should say. So there are numerous examples out there where vents were able to solve these moisture-related issues. Shown is one of those stories. The customer was experiencing ongoing issues with condensation and fogging in their antenna sensor, altitude sensor. Eventually, this would lead to buildup of condensed liquid and damage the equipment on the inside. So our vent was able to resolve the fogging issues for the life of the altitude sensor. We shared this example in the first webinar, so if you didn't get a chance to watch it live, I please invite you to watch that recording. I think there are some more in-depth conversations about this. I just wanted to touch that the condensation topic is a benefit that our venting clearly provides. Additionally, there are further examples available and will either be attached to this webinar or available for download from gore.com. I do want to point out that the security camera study includes a vent combined with a desiccant option and is a great read demonstrating the benefits of venting and mitigating the effects of condensation. If you have questions about any of these, please do not hesitate to reach out. We're more than happy to explain on a deeper level. As Michael touched on, we do also have various product form offerings, which include different benefits and performance ratings suited to be compatible with your electronic enclosure. I'd like to thank you for your attention. I hope you learned a lot today, and feel free to reach out to us for your next project. We're ready to help. Before we move on, I'd like to end our prepared remarks by reminding everyone that the third webinar in this series will be focused more on a discussion panel where you'll have the chance to ask the experts about what it takes to design electronics that can survive and thrive in the harshest environments. With that, I would like to open this presentation up to any questions you may have and turn it over to Amy. Thank you.
Thanks very much, both of you. We've got a lot of questions, but don't let that discourage you all. If you haven't asked yours yet, or you're asking this on demand, we'll make sure that those get answered. So I'll stop my chatter and jump right to them, gentlemen. And feel free to jump in, whoever wants to address the question. So the audience is asking, in one sentence, how do you define moisture management for outdoor, indoor electronics? And what's different about it versus basic IP protection? Great question.
Yeah, I think I can take this. One sentence is not very easy to summarize this presentation. One sentence. But I would say for moisture management, in one sentence, the most important thing is think about it at all and think about how you will remove the moisture out of the enclosure as it will be there. It is very hard to prevent the moisture going inside the enclosure, but think of a way to remove it after it came in. And the second part for the difference to basic IP protection. So typically for the IP protection, it is about pressure equalization. So for the pressure equalization, the pressure is everywhere the same inside an enclosure. But for the moisture, there are gradients inside the enclosure. So the positioning of the vent has a much higher impact for moisture management compared to the IP protection, where you can put it in almost any place because the internal pressure is the same in any place. But for the moisture management, you really want to think about the placement of the vent.
Okay, great, thank you. All right, we'll move on to the next one. Alec, welcome to jump in if you want to with your single sentence at any point. But the attendees talked about that you started the deck by recapping Module 1's venting basics. And again, everyone, you can find that linked in the Resource Center, okay? So gentlemen, can you briefly restate how a microporous membrane both equalizes pressure and blocks contaminants, and why that's the foundation for today's discussion on condensation?
Yes, I can certainly touch on this. So the microporous membrane, essentially the structure, it enables air to move freely through the membrane, while at the same time blocking contaminants such as liquid, dust, dirt, and debris. And why that's the foundation for today is because on top of those benefits that the microporous membrane and our venting solutions offer, we also need to consider moisture management, as they are bidirectional. But with what we shared on proper placement, we are able to manage that condensation while also still preventing contaminants and liquid ingress with the pressure equalization that all of these vents provide.
Great, thank you. Well, let's keep going here. Your slide, and I think this was yours, Michael, but your slide contrasts relative humidity with dew point. Why is dew point the better predictor for condensation risk inside an enclosure than relative humidity alone?
This is a great question. So typically you want to assess the risk of condensation. So if you take the dew point, you immediately see the difference between where we are right now with the dew point and the point where the condensation can occur. So for example, or you see where we are right now, sorry. So for example, on the left-hand side, you can see you're currently at 22 degrees C and the dew point is at 11 degrees C. You still see your safety buffer is 11 degrees C, and you immediately know it. But if you just look at the relative humidity, which is dependent on the temperature, you cannot immediately see what is your level of safety. So, for example, if you have 80% relative humidity and you don't know what's the temperature, you don't know how much safety, how much cool down you can afford before you hit the condensation point.
Okay, so it's important that the two are considered, yes? Both dew point and relative humidity. Okay, great. Okay, so the next question here. Walk us through the lab example. At 22C, at 50% relative humidity, this is the slide that we're on, right? The dew point is 11C. As temperature drops to 15C and then 11C, what exactly changes? And where would condensation first appear in a real enclosure?
So what happens if you cool down the system, or the temperature will decrease, that the air is being saturated with moisture. So the moisture can the air can take different amounts of moisture at different temperatures. So when you cool it down to 11 degrees C, you hit the point where the air is saturated and cannot take any more moisture. And to the second part of the question, where will the condensate appear? So it's always on the coldest spot of the system. So oftentimes you have a temperature gradient inside your enclosure because you have a heat source, or if there is sun radiation, you also have a warmer surface that is facing the sun and a colder surface on the opposite side. So the condensation will always form on the coldest spot of the system.
Okay, great, thank you. So our next question here, and I'm wondering if this attendee was at that the first module, because he asks, does the amount of holes cut for the adhesive vents influence condensation mitigation? I know we talked about holes in the adhesive vents last time, but this is in the context of, does it influence condensation mitigation?
So I would assume that you cover the hole with a membrane afterwards. So then the main factor, and I just quickly jump to Fick's law to show this, the main factor is the total exchange surface area. So if you have two vents with the same total size of one vent, then they behave the same, the two smaller behave the same as the larger one. The advantage of having two smaller vents would be that you can place them on different sides, on different places of the enclosure. So perhaps you don't have only one cold spot, but you have two cold spots. So then you can place two vents and divide them, each one vent per cold spot, and you protect both of these cold spots. So there would be the advantage of having more than one vent.
I see. Okay, great, thank you. We're going to keep moving through these questions. We have a lot of them, audience. And again, if we don't get to them all, you will get your answers. So you outline primary and secondary moisture sources. In typical polymer housings, how do permeation through plastics, diffusion driven by concentration gradients, and sorption on or within plastics compare to moisture transfer through the vent itself? This is a long question. You got that, guys?
I hope I got it. So this is about how sorption and permeation compare to the diffusion.
Yes, I think that was it,
yes. So, and I think this is an important question when it comes to condensation formation, because at the end, condensation formation is also a question of speed. So I will quickly jump to my 70C slide. So in this example, you can see with the dark curve that the humidity builds up rather quickly when you heat it up by desorption. And as it will build up and is not removed by the vent, you can see this is a really important factor, and as it has a very fast speed. It is faster than the diffusion through the vent. Then if you consider permeation, this is typically slower than the diffusion through the vent. So desorption has a very critical role, especially if you have a very high and very fast temperature change. Perhaps this temperature change in this example is also not realistic, but desorption can be very fast compared to the diffusion. So I would say that this is much more important compared to the permeation, which is a rather slow process and can be compensated by the diffusion through the vent quite easily.
Okay, great. Let's stay on that slide because I think that might be relevant to the next question here. So what are some early warning signs that condensation is going to be a problem? When will a problem appear? What kind of heads up do you get?
Mm-hmm.
When hopefully not when it's too late.
Yeah, so typically you can have a chance to see it by just looking at your CAD model oftentimes. So if you see high amount of plastic materials and a heat source right next to it, and especially if you designed in polyamide, the high amount of polyamide and the heat source right next to it, then you could see from the CAD model as an early warning sign that you might see some issue without even testing. Because I would assume typically the condensation testing would not be the first on the list if you develop a new device.
Mm-hmm. Yeah, definitely not. All right, so Alec, this one I think is best addressed by you. Enlighten me a bit on how the membrane blocks moisture, dust, oils, etc., and still remains optimally functional for a long time, or even its whole lifetime. I'm saying so because if it acts like a filter, filters are sometimes cleaned or replaced. Is the membrane immune to these issues present in filters?
Sure, thank you, Amy. So just a point of clarity, the membrane does not block moisture. It is transparent. It does block liquid water, dust and oils. Part of the dust and oil property is most of the membranes have an oleophobic property as well as being hydrophobic, and that's what helps prevent those types of contaminants. The membrane pore structure does lead to prevention of a majority of these small particles.
Mm-hmm.
And for replacement, filters tend to be a much higher porosity, so there's a lot more channels for dust, dirt, and debris to be lodged in and essentially degrade that filter lifetime, the filter performance over its lifetime. I don't believe we have examples where membranes had to be replaced for maintenance.
Okay.
However, in certain environments, there are instances where we will recommend pulsating the membrane in certain scenarios if there is a high dust load, for example, and that's something we can talk further about if there's a specific request for that.
Okay, great, thank you. I think we're going to get in at least one more question here, so let's jump to this. Where does desiccant fit alongside a vent? When is it complementary, and when does it just delay the inevitable condensation event shown in your dew point slide?
I can take this, and I think this is a very common question, as people oftentimes think about desiccants in the first place when it comes to condensation, but then also venting to remove the condensation. So you need to be very careful if you combine both of them, because as the desiccant keeps the internal very dry, and as seen in Fick's law, if the internal is dry, then you will automatically pull in more and more moisture, saturating the desiccant faster and faster. So typically, both of them are not a very good combination. However, there are some applications where it can make sense to combine both of them. But then typically you only have a very small vent allowing only a little amount of moisture coming through the membrane, and the desiccant absorbs whatever comes through the vent, which must not be too much. So in this case, the vent would fulfill the pressure equalization function, and the desiccant would fulfill the moisture function.
Okay, they are complementary. Hey, I think this, we have just a little bit of time left, but I think this is a great question to end on. So, and this is, each one of you have an opportunity for this one. Give us your 2 must-dos that most reliably prevent condensation-driven failures in the field, distilled from the mechanisms you covered today. So, Alec, how about you first? Give us your 2 must-dos.
Sure. I believe, of course, we're talking about venting, so the venting selection, solution, location of that venting. But I think also because of the emphasis on material selection in conjunction with the venting, that would be the most ideal 2 critical decisions to make in order to mitigate condensation.
Excellent, thank you. And how about you, Michael? Give us your 2 cents on the 2 must-dos.
For me, the most important thing would be do vent at all, because oftentimes I saw that there are sealed enclosures and people think that the moisture cannot come in, but it does. So do vent at all. And the second do would be placement for me. So do place them correctly. A vent can be very effective in the right placement, but it can also be very disappointing if you place it wrong.
Okay, excellent. Great advice. Great way to end on that. But just remember, audience, that's not the last that you've heard from these 2 guys, and some more folks from WL GORE. So just keep in mind that, let me just get to, here we go. Just keep in mind that we will have the 3rd module, and in December, make sure that you use the links in the Resource Center to catch that one. And also remember that you can still ask questions from today's event. And we ask if you could take a moment just to complete our survey. We do appreciate you taking part in the poll questions, and for everybody hanging out. And obviously you all need a shower, so I would suggest maybe that's the next thing you do. But again, remember the webinar will be available on our website, and please check out the other modules. They're very, very complimentary, speaking of complimentary, and a great background, and that will just give you grist for your question mill to ask the experts in December from WL GORE. Hey, gentlemen, Alec, Michael, thank you very much. Excellent presentations. Lots of great questions. Thanks to the audience for hanging out. We all did. Yeah, honey, thanks very much.
Thank you, Amy.
Thank you.
Cheers, guys. Bye, everyone.